give an assignment in lab that's going to be due, probably due Monday. So I'll give it to you Thursday. All right, so that's it. In the meantime, in order to be able to name ionic compounds, we need to talk more about ions. Okay, so that's what we're going to do today. Actually, I want to get to like slide 27 or something and then skip to part 3 today, if that works for you guys. Okay, so we're in part 2. And a lot of this is review. And I'm like, sometimes review students shouldn't say just students, everybody's mind sort of wanders when you're talking kind of in review mode. And this class very much builds on itself. You know, a lot of sciences do. So notice this concept of valence shell electrons. You're like, wait a minute. How do I know anything about that? Well, in order to know valence shell electrons, you have to know how to set up electrons, how to configure electrons. And you guys did that on your last unit exam quite handily for most of you. So you need to set up how electrons are configured, and then you identify the kind of the electrons that are in the highest, the subshell with the highest number, and those are your valence electrons. Okay, so that's kind of one of the things we talked about before. So you might be saying, oh my gosh, you mean I have to do electron configurations of everything and to identify valence electrons? Well, not in this unit. Maybe in unit 2, but not in unit 3. Here is the secret, or a secret. It's not really much of a secret. But if you're talking about the group A elements, and I kind of have an excerpt down here of your periodic table, okay, we're using. If they're the group A elements, all you got to do is look at the group number. The group number. So 1A, the group number is 1. So that has 1 valence electron. 2A, 2 valence electrons. And we skip over here, 3A, 3 valence electrons, 4 valence electrons. You get the idea. Cool? Okay, those are valence electrons. That's awesome. Right.
And I'm guessing the transition metals throw it all off.
Well, the transition metals, it's kind of interesting. I'm glad you brought that up because I think you had a test question about this. Actually, all of these guys, because these are what we call N-1, D block, right? D block. And these are F, or N minus, they're down here. Down here, the F block are N-2. When we're adding electrons, kind of skipping across the periodic table, here, they actually are not valence electrons. So long story, these all have 2 valence electrons. I know it seems kind of weird if they're using the lowest N plus L rule. 2 valence electrons if it's the lowest N plus L rule. Kind of weird. That's just kind of how it works. Okay, but for the group A elements. And then a lot of times, you know, your eyes glaze over when I talk about atoms want to get a complete octet. You know, you're kind of familiar with that. The 8A elements, they have, remember, oops, sorry, go back. The 8A elements, okay, I put 8 electrons at the top of their column, okay? That is a complete octet. And you guys told me, octet, yeah. You guys told me that the name of those actually over there with helium, neon, argon, krypton, xenon, and radon, those are all noble gases, rare gases. Inert gases, the inert material in your medicines doesn't do a thing for you, right? So inert gases don't like to play with anything else. Okay, so here's the deal, and I have this website down here if you want to jot down periodic table web. Actually, I posted it on my Twitter feed, and there are, how do I say this? There's also there's an app for that. There are also apps, and my app was free for the Apple product, and I bet it's got an Android product too. But periodic table web, it's great. I'm going to take us out there here in a minute. But for all of those rare gases, noble gases, inert gases, if you were to say how all the electrons are configured, it would peter out with this. It would peter out with the valence shell, okay, so the highest N, it would be an S subshell with 2 electrons and a P subshell with 6. Okay, so 2 plus 6 is 8. There's your octet. Okay. So when we get to talking here about an atom wanting to lose its valence electrons, or an atom wanting to pick up valence electrons, what they're doing is trying to get a complete octet, and I'll try to kind of convince you of that. But in the meantime, check out this website. And you're like, dude, if I could have any website for an exam, I might would pick this one. Let's see how the internet's doing today. Not bad.
It's just periodictable.com.
Yeah. Yeah, ptable.com. And actually my app is ptable. But the thing about my app, some apps, as you guys know, you can do offline or online, like have connection to the internet or not have connection to the internet. My app, I really like it, but I need to have connection to the internet. So here we go. Just to kind of orient yourself, yes, it does use Wikipedia. I kind of like Wikipedia. Okay, but those tabs across the top, properties, orbitals, isotopes, we talked about isotopes. Compounds might come in handy. I'm going to click on orbitals, okay? And orbitals will, you guys see the familiar, let's see if I think I can write on this. Okay, you guys see the 1s, 2s, 2p, 3s, 3p, 4s, 4p, okay, and then the 3d is kind of inserted in there. Okay, so right now it's clicked on hydrogen. How many electrons around a hydrogen? 1. Where is it? In the 1s, right? So let's pick on fluorine. Okay, fluorine, just for kicks, let's see, what do you think? It's right next to neon, so it's 7A, right? They don't have the kind of the old convention. But if I click on fluorine, it's got 9 electrons. Where are those 9 electrons? Here are the 9 electrons, exactly what we've been talking about. 2 electrons. Notice the arrows for the electrons. Isn't that adorable? The boxes for the orbitals. Arranged in subshells, exactly what we talked about. So 1s2, 2s2, 2p5. Does that look right? Okay. So 7a, can you see the 7 valence electrons? Okay, 7 valence electrons would be right here. Right? Okay. So that's what I mean by valence electrons, and this is a great website. Let's go back. See, where did it go? I want to go show you the compounds right quick in case I forget later. It is so cool. I was playing around with it the other day. And it is so free. Let's see, it's not. There we go. So if you click on compounds, let's see, I used it on my iPad. Let's see how this works. There should be a place. Oh, here it is. It says name or formula. Oh my gosh. Some of you guys are familiar with benzene. I could put C6H6, and there's probably more than one compound that has that formula. It's a weird world out there. Okay, but benzene was what I was after. Okay, I could click on there, and I can say the name or give you some information. We're going to be talking about nomenclature today, or today and tomorrow. You guys would tell me this is table salt, right? NaCl, what's its name? Sodium chloride. Okay? So don't you think this would be a nice one to have on your test? No, you cannot have it on your test. Okay. But that's kind of how that works. You can also put in the name, like ethanol, and it'll spit back. Ethanol. Ethanol. Oh, okay.
On methanol.
I know. I don't know why that is.
Silly.
Got another.
Wait.
I know.
There it
right?
is.
And so, yeah, it's off of Wikipedia, so it'll give you some cool stuff about it. Ethanol is a little bit bigger than methanol. I can never remember which is which. Methanol is the simpler one. So, I don't know. It's a thought. In the meantime, back to what we were talking about. Okay, so that's periodic table web. And there are apps, I know. So I thought I would go ahead and we've seen, okay. So here we go. There's two types of monoatomic ions. There's positively charged ones. Okay, so these are positively charged ones called cations. And the only thing that can come and go when an ion is formed is electrons. Only electrons can be, I kind of think of an electron as being kind of rubbed off, or electrons as kind of being dumped on the outside. You're never going to get a difference in charges of something, of an atom, by changing the proton. So it's only electrons. So if something's going to be positively charged, that means it must have kicked off an electron or two or three. Okay? Anions are negatively charged. Okay, so cations have lost one or more electron, and anions have gained one or more electron. So it kind of makes sense. A lot of things in chemistry I don't memorize personally. I just kind of think through it. I'm like, oh, okay, well, that makes sense. And not to be confused with a cation and an anion, but that's kind of what they look like, a cation and an anion. All right. So just like, well, I mean, we've kind of come full circle, I think, a little bit. In that little video that we've watched a few times for table salt, okay, it always shows you kind of the electron being transferred from the sodium to the chloride. The sodium is the metal, and the chlorine is the nonmetal. The other thing, I don't know if you guys remember this, but when we talked about electronegativities, check this out. I love it. We said electronegativity is this symbol, right? Electronegativity. We said that metals have low electronegativities, meaning that they're like, hey, I don't want that electron. I'm like, dude, I'm so ready to get rid of that. And so that's kind of consistent with this too. Low electronegativities, high electronegativities. Okay? And the chlorine's like, bring it on. But now we're going to kind of introduce something, kind of bring it full circle, this octet. In transferring, the sodium gets an octet. In transferring, the chlorine gets an octet. Let's see how that works. But before we do, so do you guys recognize, let me grab a red here. Do you guys recognize this? Where X is the symbol of the element, and we have two numbers on the left side. In the upper left, it is what we call the mass number. So that's protons plus neutrons. And the lower left is optional. Actually, that's the number of protons. That's the atomic number. Well, what's new here is, dun, 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 we can have a cation or an anion. And I think I told you guys the ones you did for your test were neutral. And I kind of circled up there in the upper right-hand corner. I said there's nothing there. Not a plus, not a minus. Okay, they're neutral. Well, let's see how this works now. And we're going to do a couple of examples. And this will also be on your test. Don't you love it when you come to class and you're like, I know what's going to be on my test. Okay? So again, I'm going to give you the symbol, in this case for calcium. And we see the big number in the upper left, the smaller number in the lower left. Okay, we know by subtraction we can get neutrons. Remember we talked about that. Because the big number is neutrons plus protons. The 20 is kind of redundant, quite frankly, because it's the same one as you can get off the periodic table. Robert?
You're supposed to say 39 because ours says 36.
Oh.
Mine says 39. Mine's 39.
Oh, my gosh. Did yours say 36?
Yeah.
That is so crazy. You got to say
I think you're looking at the wrong one.
yeah. This one.
Okay.
Good catch, though. Very good. So what do you think? How many protons does it have? 1, 2, 3. Shout it. Okay, 1, 2, 3. 1, 2, 3. How many protons?
20.
20. Very good.
Dang, I was so I mean, like, your timing off.
Oh, okay. Yeah, I'll do better this time. This is the first time doing this. Okay. So electrons. Now, before I say how many does it have, now I'm going to ask more or less. So my question is going to be, does it have more electrons than protons, or does it have less electrons than protons? You're right. Why? How'd you know that?
Because it's positively charged by 2.
Because it's positively charged by 2. It has less electrons. Very good. So I think we'll do this on the count of 3. How many electrons does it have? 1, 2, 3.
18.
18. Very good.
I just suck at it. And
Well, it'll come. We just keep working because I think you're going to have some homework coming up on this stuff too. So, all right, neutrons is one of the things we talked about before. It's by difference. Kind of get your calculator out if you want to. I'm going to ask you how many neutrons on the count of 3. 1, 2, 3.
19.
19. Very good. It's a version of doing a quiz thing. Very good. Okay, let's do another one. Chlorine. All right. How many protons on the count of 3? 1, 2, 3.
17.
17. Very good. Does this have more electrons or fewer electrons than protons?
More.
It has more electrons. Why?
Because it's negatively charged.
Because it's negatively charged. Very good. How many more does it have?
1.
1. Okay, number of electrons. Count of 3. 1, 2, 3.
18.
18. Very good. Get your calculators out if you need them. This is one of the things we talked about with isotopes and all that neutrons can kind of come and go. But we know we can get neutrons by subtraction. So, how many neutrons on the count of 3? 1, 2, 3.
19.
19. Very good. I would have had to do that on my calculator. Very good. So I'll be able to do that. Okay, and this is some practice doing that. I'm not going to pull these up right now. I think you'll be fine with them. You can always, well, you'll see me tomorrow if you have any questions about these. So these will be due on Friday. We're going to keep going. All right. So these are all in the same period. Carbon, nitrogen, oxygen, fluorine, and neon. They're all in period 2. So actually they're kind of going from left to right. And here's my hint, or not a hint, but to kind of make a point. This is 4A, carbon's 4A, 5A, 6A, 7A, whoops, A, 8A. That's the group number. So guess what those dots are?
The valence electron.
They are the valence electrons, exactly. Okay. And I have kind of an explanation to what your textbook does a little bit different than how I learned it. I think your textbook calls these Lewis structures, and I call these Lewis dot formulas. Okay. And I reserve the word Lewis structures for something that has more than one atom, so I'll kind of show you that later. But yeah, the symbol represents basically, you figure the center of the atom, the nucleus, and the symbol also then represents the non-valence electrons. And I like to kind of pretend like, well, not pretend, but like if you had a kid who's playing with a car, and the kid's going to park the car in a parking ramp, okay, I kind of almost think that, can you see around that carbon? It can park it here, it can park it here, it can park it here, it can park it here. It's almost got like 4 slots it can park a car, okay? Down over here, fluorine is one of those halogens. It can only park 1 car. Okay. The other thing is this slide says there's no difference between those north or south or east or west. Okay. But you can kind of clearly see how many cars you need to park to get a complete octet. Okay. So here's my little explanation about in my slide about those Lewis electron dot formulas. Okay, it's really not too much of a big deal. What we'll need to spend some time on, and actually I think that'll be next week's lab, is drawing Lewis structures. And Lewis structures, to me, actually is something that has more than one atom. Okay, all right. So let's look at some pictures of some atoms, and let's look at their Lewis dot formulas. So helium is atomic number 2. Okay, so it has 2 protons, we learned last semester, and if it's neutral, it has 2 electrons. And here they are. Okay, and actually, helium's kind of a weird one because it's so little. Actually, it's over in 8A, which is like it doesn't have 8 valence electrons, it only has 2, right? It's kind of an exception. Sodium. Sodium is in group 1A, thus the Lewis dot formula for sodium with its one valence, cute little one valence electron there. Okay. Now we've been seeing in animation that sodium, when it combines with chlorine, loses an electron. That's the electron it loses. Okay. It loses that actually. It's a 3s1 electron. It's in period number 3, and it's an s block. Okay. So it loses an electron and becomes positively charged. Loses that 3s, that one electron 3s. Okay. And then actually, this is easiest to kind of show you with the full electron configuration. But when it loses that, now it has a full 2s2, 2p6. Okay. So that's its octet. So basically, it lost one, and it kind of looks. Oh, well, what was not valence now is valence, right? Because it lost one. All right, it's lost its entire valence shell. Fluorine, of course, it's a 7A element. That's the 7 dots around the fluorine atom. And fluorine, if it wanted to form a cation, you're like, dude, really? It would like to have to kick off all 7. But it's easier to form an anion. It's easier to form a negatively charged ion. Just bring in one, and that's what it does. And it gets its complete octet. Okay. Notice the kind of convention we're going to actually use next week when we talk about Lewis structures is if you have anything charged like that, you really do need to put it in brackets and kind of put the charge outside. All right. Sulfur. I don't even look at the periodic table. What do you think? 6 dots, 6A? Yep. So to get a complete octet, gain 2 electrons, exactly. And this is what it looks like with its this is its ion form, sulfur. It's exciting. Okay, so these should be pretty straightforward too. And I don't have them to pull up handy for you right now. Okay. So sometimes students will, at the top of their periodic table, I don't have a periodic table here to show you, but sometimes at the top of 1A, they'll show +1. Okay, and that +1 is the sort of charge it forms. Okay, why? Because it kicks off its one valence electron. At the top of 2A, sometimes they'll show a +2. Why? Because that's the charge it forms when it kicks off its 2 valence electrons. Sometimes 3A, they'll show a +3. Okay? Notice, and I'm going to try to convince you of this and explain this again in lab. Notice the 4A column, I don't have anything there because it's kind of a little bit of a wash with carbon and those things. They can go either way. And then what I usually like to do is, also over here, there's no ions formed. No ions. Why? Because they have a complete octet. 8A. Okay. This is your 7A, and we said it's going to pick up 1 electron, and it's going to form a -1. Those were your halogens. Oxygen, sulfur, selenium, and tellurium, they have 6 valence electrons. Okay, and they need 2 more electrons. They're going to form a -2. And then last but not least, nitrogen and actually phosphorus underneath it for sure. The JAG gets a little iffy. Things that are on the JAG are like, I don't know. Okay, but for phosphorus, too, it forms a -3. All right, so actually these next few slides just reinforce what I just told you. So if you want to know how many valence electrons an atom has, all you got to do is look at its group number. Valence electrons for the A elements is its group number. Okay, so 1A elements have 1 valence electron, 2A elements have 2 valence electrons, 3A elements have 3 valence electrons. Now, metals have a low electronegativity. Metals are like, dude, yeah, I'm going to kick off all of my valence electrons. Metals do that. Non-metals don't. Okay, that's why when I started with, if you look at 3A, unfortunately, 3A is on the other side of the transition elements. So 3A is like, it's got the jag going on, right? So 3A, boron is a non-metal. Aluminum's a metal, gallium's a metal, indium's a metal. I think that's thallium's a metal. Those things will lose electrons. Oops, did you get all that? Okay. So again, this is just looking at what I told you or summarized ahead of time in a different way. These are all one family. So this is 1A elements. So lithium, sodium, potassium, rubidium, and cesium will form a +1 charge. Why? Because they'll kick off their valence electron. Are there neutral atoms of these things? Yeah. But given a chance to get a complete octet, this is how they're going to do it. Kick off one electron for a +1 charge. Going over, so those would be the alkaline metals, the alkaline earth metals, or 2A, okay? 2A means 2 valence electrons, kick them both off, become a +2 cation. So that would be beryllium, magnesium, calcium, strontium, and barium. I just think barium's lighter than that, but barium's really pretty heavy, isn't it? So with 3A, I'm going to skip boron. Does that make sense to everybody? 3A, because I'm only talking about things that are going to lose electrons, and those are the metals, and boron's not a metal. Okay? So for the 3A, and it looks like I'm not going out on a limb, I'm not including indium or thallium. Not quite sure why that is. But aluminum and gallium, 3A, 3 valence electrons, kick all 3 off and become a +3 cation. Sometimes the way I think students have told me they remember cation is that it's like a T, like a plus. So they're positively charged. Okay? So dots dot. So now you got some ideas on how you might want to kind of, when you get your periodic table for your test, kind of do something with the columns. So let's take a closer look at what's going on with the electrons. And of course, this is one of the things we talked about last unit. Sodium is atomic number 11, so it has 11 electrons, and this is how those 11 electrons are configured. So 2 + 2 + 4 is 10, +1 would be 11. So those are how all of those electrons are hanging out. So you would tell me the valence electron, there's only one in the 3s subshell. And that's actually the one that's going to go. So sodium, you would also tell me that it forms a +1 cation. Okay, so one of the things you're going to want to be able to do, another thing you learn for your unit exam coming up, is we wrote electron configurations of neutral atoms before. Now you need to be able to write electron configurations of ions. So what on your test I'm going to do is I'm going to give you an atom like sodium. So I'm going to ask you to write the electron configuration, and then I'm going to tell you a cation, okay? And you're going to have to kind of show me what's different between those two. So obviously what's different is this went away. Okay, that was the valence electron. That one is gone for that. So let's do another one. So one of the things we talked about last unit was, again, how do you come up with how the electrons are configured around a neutral aluminum atom? You know it's neutral because there's nothing up here, right? And so, of course, you would look at the periodic table and you say aluminum looks like it's atomic number 13, so I need to find homes for 13 electrons. And this is what they look like. So aluminum is 3A, so it has 3 valence electrons. And the cool thing about writing its electron configuration is you can see where those 3 valence electrons are. And so actually, here when we write the electron configuration for the aluminum cation, not so surprising, what's not there now are those 3 valence electrons, 2 in the 3s and 1 in the 3p. So be able to kind of do that. I'm a firm believer in, for this topic, giving you the neutral atom and then the ion, the neutral atom and then the ion for the electron configuration. All right. Switching over to the non-metals. And again, 4A, we're not going there. We're just going to go with 5A, 6A, and 7A. And 8A don't form ions, right? So the nonmetals are going to pick up electrons. They have a high electronegativity, and they are going to form negative anions. So if we take a look at them, beginning with the 5A nonmetals, and just the first two, again, I think it extends to astatine and antimony, but I don't know, acetine's on the jag, isn't it? So maybe not. Okay, so these are 5A. 5 means 5 valence electrons. How close are they to getting a complete octet? 3 more. Wait a minute. 5. There we go. 5. How close? 3 more. Right, exactly. Okay, so skipping over from 5A to 6A, the 6A, just the nonmetals now. So we're not going to go underneath the jag. 6A nonmetals. 6A means they have 6 valence electrons. They are 2 away from getting a complete octet. That's why they form a -2 charge. And right underneath sulfur would be selenium in the next period. And again, I'm just not quite sure. I think selenium might tend to form a -2 anion too. And last but not least are our halogens, our 7A elements. 7A means they have 7 valence electrons, so they're 1 electron away from getting a complete octet. So that's why they form a -1 charge. These are halogens. I love the halogens. So let's look at electron configurations of anions, the nonmetals. Picking on chlorine, we're going to use the abbreviated rare gas notation. It works really pretty darn well. So if you find chlorine on the periodic table, it is in period 3, and in period 2, the rare gas is neon. So at the end of the row B above it is neon. Okay, that would be 10 electrons. And so then the electrons beyond neon are here for a neutral chlorine atom. So we said chlorine tends to form a, let's see, I'm going to ask you on the count of 3 what charge it forms. A negative charge. Count of 3. 1, 2, 3. Negative.
2.
No.
No.
-1.
-1. Why is it a -1?
Because it only needs 1 electron.
Because it only needs 1 electron. Exactly. -1, 2, 3. Yeah, it has a -1. The other thing is, can you kind of see why it forms a -1 charge? Because this is how the electrons are configured. To get the 3s2 3p6, it only needs 1 electron. So, of course, to show a chlorine ion, we're going to call it a chloride ion here soon. We would show -1 up there. And you guys know that if there's no symbol here, that means if there's no 2, it means -1. Okay. So yeah, here's how the electron configuration of the chloride actually anion looks like. So you can put the rare gas of neon, and beyond neon it's 3s2 3p6. And voila, there is your complete octet right there by picking up 1 extra electron. So kind of be able to write those pairs of electron configurations too. We'll do one more of these nonmetals. Okay, and we'll pick on phosphorus. Again, periodic tables are, for tomorrow's lab, you're probably going to want to have a periodic table handy. You might even, for tomorrow's lab, want to have one that you're starting to mark up to memorize so you can kind of recreate it on your test if you want. But phosphorus is in 5A, it's right under nitrogen. So we know it has 5 valence electrons, here they are. Okay? And it's easier to pick up 3 to get a complete octet than to kick off 5 and form a cation. That's kind of the way I look at it. But nonmetals form anions, they pick up electrons. So it's going to pick up 3 electrons. So on the count of 3, I'm going to ask you what charge it forms. 1, 2, 3. -3, yes. So there's the phosphide. We're going to talk about that. Actually, phosphorus anion is called phosphide. And picking up 3 electrons, here's what it looks like. It has the core neon, and then it goes 3s2, 3p6. So, of course, the difference here is kind of in those electrons. It's all right? It's all right. All right. I like this topic. So if I were to, and sometimes I think I told you in lecture these would be vocab words, and they don't end up being vocab words. But this is one of my favorite vocab words. I just like the idea, isoelectronic. So as we've been talking about metals giving up electrons, okay, and nonmetals taking in electrons, there's quite possible that actually you can have things that are different species with the same number of electrons. So to give you an example, kind of centered around the noble gas neon, okay, neon has 10 electrons, has complete octet, okay, and so here's what neon looks like. 2 electrons in the 1s, 2 electrons in the 2s, 6 electrons in the 2p, that's neon. But here's the cool thing about it, the nonmetals in the same period, nitrogen, oxygen, and fluorine, they pick up 3 electrons, 2 electrons, and 1 electron to get that same configuration. These over here, these are the metals in the period after it. You're like, where's sodium, magnesium, aluminum? Well, they're actually the period after it. They lose electrons to get that same rare gas configuration. Those are called isoelectronic. I think that's so cool. Okay, so what we've been talking about are these 1As tend to form +1 cations, 3As, and actually we at least went under aluminum, which was gallium. Okay, form +3. Then we talked about the halogens, form -1 by picking up an electron. Oxygen and sulfur pick up 2 electrons. Nitrogen and fluorine pick up 3 electrons. Okay. What we haven't talked about, I'm just going to go ahead and put an X through them right now. Okay, where I have X's there, right? They fall under a couple different categories. But for instance, if we pick on iron, iron's got a couple things it can do. Iron can actually lose 2 electrons, or iron can lose 3 electrons. Okay, and this is kind of what Cameron said, that, these are kind of like, I don't know. And actually, tomorrow's lab will try to kind of give you some hints on how you handle that. All right. So, let's just say you go to kick off electrons, okay, and you're only going to kick off, say something has 3 valence electrons, and you're not going to kick off all 3 valence electrons. Well, this simply says that the first to go is going to be the one with the electron in the subshell with the highest L value. So here's where I need to remind you, again, this class just kind of builds on itself, like a lot of physical sciences. Remember, you guys would tell me the subshell types are S, P, D, and F. Okay, and we said values, what we actually call L values, are 0, 1, 2, and 3. So this is to say, I'm going to show you an example. For instance, if we pick on, let's see, we did aluminum, okay? Or did we do, yeah. Let's pick on let's pick on magnesium. Okay, magnesium, for instance. Okay, it's atomic number 12, and its electrons are configured like this: 1s2, 2s2, 2p6, 3s. No, that's not a good example. That's going to pick on. We do have to go over to aluminum. Final answer. You'll see why. Okay, so aluminum has 13 electrons. Sorry about that. 1s2, 2s2, 2p6, 3s2, and then 3p1, right? So actually it's a 3a element, and there's where its 3 valence electrons are. Okay, and we know it forms a +3 charge. But what this slide is saying, when it comes time for those 3 electrons to go, actually the first one to go is the electron in the 3p, because p is got a value of 1. And in the 3s, those don't go first because s has a value of 0. That's all it is. Okay. And I'm trying, it's kind of a subtle thing. I'm trying to think, I don't think the way I ask questions on your test, it ever comes into play, really. So you're like, why do you tell me? Well, because in case you go on to major into chemistry, you need to know these things. All right. So an example of that, I think, well, actually, do you guys remember a minute ago I said iron forms two different, it can go and lose 2 electrons, and it can also lose 3 electrons, an Fe plus 2 and Fe plus 3. Well, let's take a look at that. So iron, in astronomy, we're all about iron, right? Because in astronomy, in stars, that's actually the heaviest element that stars can make in their cores. It's so cool. So there's 26 electrons here. Okay, you can count them if you want to. But notice that, can you see the valence electrons? And actually, they're easier to see when I do it this way. One of the things we said, if you go ahead and come up with electron configurations, is you can reorder them in order of increasing n, and that's all this is. So here, clearly, you can say the highest n is 4, and so we have 2 electrons and 4 s subshells. 2 valence electrons. Just like I told you, remember? I said all the transition elements have 2 valence electrons. All right, so when iron forms that plus 2, okay, guess which one does? This one, right here, these 2 electrons. I should say which one, I said which 2 though. Okay, it loses 2 electrons. Okay, so for the plus 2 version, the iron cation, its electron configuration is without that 4s2. So it goes 1s2, 2s2, 2p6, 3s2, 3p6, 3d6. So isn't this kind of weird? This always kind of, I never entirely know how to handle this, but can you see we're actually now, we have kind of a, I think this is maybe what we call an expanded valence, but we have the lowest n is 3, and so actually we have 3 subshells like that. I like to think of it stepwise, so now we're going to go on to the other version of iron. The other version of iron, if we can kind of compare them back to back, is losing 1 more electron. All right, the last slide I told you the value of S is 0, the L value of S is 0, the L value of P is 1, the L value of D is 2. So guess what? It's going to be this one, or one of them, if those 6 electrons are going to go. So for the iron plus 3 cation, you're looking at 1s2, 2s2, 2p6, 3s2, 3p6, 3d5. And one more thought, or at least one more thought. Here's the deal. When we talked about D-type subshells, well, let's do it this way. S-type subshells, P-type subshells, D-type subshells, right? I got 5 boxes. So do you think it likes this? Kind of a half filled? I do. And so it's kind of cool, like what's going on behind the scenes. It's like, it all makes sense. Why it has 2 forms. Okay, so we actually ran out of time, but notice that actually in lab tomorrow we're going to have to kind of, if you want to bring your notebooks you can, because I'm just going to dive into probably some slides that are in the next part 3. So I'd bring your lecture notes and your lab notebooks and your brains. We'll see you tomorrow.